Welcome back. This is another exciting episode of Mr. Takeda Teaches Algebra. I'm your host and teacher, Mr. Takeda, and this is lesson 6.4 on exponential growth and decay, wherein we ask the question, what are some of the characteristics of exponential growth and exponential decay functions? Okay, so we've talked, this is another type of function we've been looking at. We've had exponential functions. Now look at growth and decay. We've seen some of these things before, but let's go ahead and take a look at exponential growth functions here. The final amount, y, I'm going to write this a little bit bigger so you can kind of see it here. Y is our final amount equals A, the initial amount. 1 plus R. 1 is, this whole thing is the growth factor, right? This whole thing is the growth factor, where R is the rate of growth, and the exponent t is time. Okay, and we're talking about equal intervals of time here. So it's either like number of months, number of days, number of weeks, number of years. It all kind of depends. This whole factor, again, factors are things that are multiplied. 1 plus R, it's greater than 1, so this is going to be growth. Get that in your notes. Let's try and apply it here the best we can. The inaugural attendance of an annual music festival is 150,000. The attendance, Y, increases by 8% each year. Write an exponential growth function that represents the attendance after T years. Okay, so we're going to do that by saying that Y is equal to A, the original amount is 150,000. And this growth factor is going to be 1 plus 0.08. That's our 8% growth every year. Times time. Okay, so I'm going to simplify this over here. Y equals 150,000 times 1.08 to the power of t. And that's our function. Now it says, how many people will attend the festival in the 5th year? Round your answer to the nearest 1,000. Okay, so that's just a matter of substituting 5 for t. And 1.08 to the, oops, I'm going to do a correction here. This should be a 4. This should be a 4. I'll explain why. Because the first year is year 0. So if the first year is year 0, right, this will be a 1, so it doesn't change anything, then the 5th year is actually a 4 in our exponent here. Okay, so 1.08 to the 4th power. I need a calculator for this. 1.08 to the power of 4 equals 1.36. So times 150,000. 204,073. Okay. So that's a growth function. Let's take a look at a decay function here. Now, decay function is very similar, except this decay factor here, 1 minus R. Now, R is the rate of decay in decimal form. Now, notice that rate has to be between 0 and 1. It can't be greater than 1. If it's greater than 1, then this thing will be negative, which we don't want. So let me write this a little bit clearer for you again. 1 minus R, that whole thing is a decay factor, and T is time again. So the rate of decay in decimal form has to be between 0 and 1. It can't be greater than 1, otherwise this thing would be negative. Okay, so let's take a look at an example. Here, first of all, let's ask if the table here represents exponential growth or decay or neither. Well, we learned previously about having a common factor for a geometric sequence. So what's happening here for A, 270 to 90 to 30 to 10, this is what? Divide by 3. Or I could say multiply by 1/3 if I wanted to say multiply by 1/3, either way. Divide by 3, divide by 3. So this has this common factor here. So this is exponential decay because it's actually getting smaller. Okay, over here again, 0, 1, 2, 3. These are evenly spaced out. 5, 10, 20, 40 times 2. 5 times 2 is 10. 10 times 2 is 20. 20 times 2 is 40. So this one is exponential growth. Okay, growth because it's getting larger, and decay because it's getting smaller. We want to look at some examples here where we're determining whether a function is growth or decay. And just looking at these, this is pretty easy to do because these exponents of t are just kind of the same here. I mean, there's nothing, the exponent doesn't change anything inside here. So we're looking at this this factor here. If this factor is greater than 1, remember that growth factor was 1 plus r. So if it's greater than 1, this is growth. This one's less than 1. Remember that for decay, it was 1 minus r. So this is going to be decay. And so we can see here at that growth factor of 1 plus r, if I set it equal to 1.07, I know that r is equal to 0.07. So I have a growth rate or percent of change of 7%. Over here, if 1 minus r equals 0.98, I know that r is going to equal 0.02. And this is decay of 2%. 2% per t. Well, we don't know what t is. T is probably a year or something like that. But that's an easy way just to kind of look at these real quick and know if it's growth or decay. We'll have some others later on where where the exponent isn't just t, so it's going to get a little more complicated. Like these. In this case, we have t divided by 4 and t minus 3. So we have to think about our rules of exponents here as we apply these. So we want to know whether or not each function represents exponential growth or exponential decay. So the first thing I want to do here is we have to kind of rewrite this and think about this in a different way. So what I want to do here is think of this as 0.96. Think about our rules for raising to a fractional exponent, and we're kind of going backwards here. So I'm going to think of this as 0.96 to the power of 1/4, and the whole thing now will be raised to the power of t. So I get that t by itself again, right? So the fourth root of 0.96, I can think of the fourth root of 0.96 as approximately This is going to be an approximation after this point. 0.99 raised to the power of t. So there's my function, and this is actually exponential decay because, again, this is less than 1. So this is decay. Over here, let's take a look at this one, f of t. I'm going to think of this as t minus 3. Think about our rules of applying exponents to a quotient. Okay, so I can think of this as 1.1 to the second power over 1.1 to the power of 3. Right, so we subtract those to. I'm kind of going backwards on simplifying a quotient here with the same base. And now to simplify this, I can do 1.1 to the third power. As 1.1, 1.1 to the third power is 1.331. And I want to move this out of here, so I'm going to think of the inverse of 1.331. So I'll think of it like this to make it just a little easier to think about in the calculator. And that's going to come out to be approximately, so I'm going to use the approximation sign here, 0.75 times 1.1 to the power of t. Okay, so this one, because it's greater than 1, this is growth. And actually, you see that didn't really change much at all, did it? From 1, it's 1.1 and it stayed 1.1. Okay, let's move on. Compound interest. Now, this is a really big idea because, well, this is how money grows in banks, even though banks don't really pay a lot of interest anymore. But when you invest in something, you know, the money that you earn on your investment gets, you can get interest on that as well. So the idea of a compound interest is you earn interest, and then you earn interest on your interest if you keep the money in the bank or wherever you have it invested. So P is principal. This is your initial amount. 1 plus R here is the interest rate in decimal form. N is the number of times interest is compounded per year. So if it's compounded weekly, that would be a 52. If it's compounded monthly, that would be a 12. If it's compounded annually, that's 1. If it's compounded quarterly, that's 4. Okay, and then T is the number of time in years, how many years go by. Okay, so let's look at a problem here. You deposit $100 in a savings account that earns 6% annual interest compounded monthly. Okay, so write a function that represents the balance after t years. Okay, so here's our form again. Y equals P, and then 1 plus R over N. That's all to the power of N times T. Okay, so we start with $100. That's our principal. That's what we started with. The rate here is 6%, so 0.06. Remember, we said decimal form. And N, we said N was the number of times it compounded per year. Since this compounds monthly, this is a 12. And then this will be 12 times T, so T years. We're leaving T because it says to leave this as T here. Okay, so let's go ahead and simplify this the best we can here. So 0.06 divided by 12, 0.005. So this will be 1.005. The whole thing is to the power of 12. And that's our and this is our function. All we have to do is write the function, and we put it in that kind of standard form that we have there. Okay, that's it. We've got some more types of problems to look at in class, but those are all the basic ideas here. And I'll see you in class. Waka waka, bye-bye.